Hi everyone, this is the preview lecture for lecture 2. Yes, in the previous lecture, we have talked about the infinite potential well problem. It was simple and analytical, but however, our goal is not provide the analytical solution of infinite potential well problem. Our goal is to provide a way to solve same problem by using numerical means, a certain type of computer aided ways to solve the same problem. Anyhow, since Laplacian operator is the central operator related to the Schrödinger equation, in this time we will try to find out eigenvectors and eigenvalues of Laplacian operator. Laplacian operator in 3D would be looks like this. It has directional second order derivative along x direction, y direction, and z direction. So if we apply the Laplacian operator to a certain scalar field psi, then it will generate certain another scalar field psi prime. So there is no guarantee that actually this resultant scalar field psi prime is proportional to psi itself. However, if we have an eigenvector of this Laplacian operator, we have the proportionality between our Laplacian operator and the original eigenvector. So this is the 3D case. However, we can make a simplification for 1D system. If this coordinate is denoted as x, then we can simply say that Laplacian operator is simplified as just a second order derivative with respect to x. Yes. So this is quite simple and straightforward. So we will try to find out the eigenvectors and eigenvalues of this second order differentiation operator. So where can you find it? Already we have discussed that the infinite potential wave problem can be casted into this eigenvalue problem. Here we have certain function, and when we take the second order derivative of this function, then it generates the original function once again and having certain eigenvalues. Here eigenvalue is minus k square and eigenvector is psi. And you know that the solution was, what was it? So for example, with the boundary condition considered in this case, something like at x equals 0, it should vanish. X equals a, it should vanish. Then we have a certain eigenfunction like this, n pi x a, and here we have a corresponding eigenvalue that was nothing but just minus n pi a squared. So in this lecture, we wanted to calculate the same solutions like this, the eigenvector and eigenvalue by using computer program. So our goal is it's a discretization. How can we discretize it? That is our question. So discretization, originally we have to work on the continuous domain. For example, in our original problem, the domain is just larger than 0 and smaller than a. Every position inside this range, we have to satisfy our eigenvalue problem. However, if we try to support such kind of infinitely large number inside this range, that would be certainly beyond our computational power. You know, although we have a powerful computer, however, it has limited memory. Yes, it has a huge memory, however, its capacity is finite. It's not infinity. So we cannot support this infinitely large number of points. So that's the reason why anyhow we have to introduce certain limitation about our capability. Once we have an analytic solution, for example, a times sine and pi a over x, then at every or at any x value, we can find exact solution. This is the power of an analytic approach. However, when we work with a computer program, we have to compromise. So in this case, without arguing that every x value is accessible to us, instead we will say that there is a certain list of x positions where we can find the solution. So let's say that we have, for example, n equal to 100. Then we can have the solution for this domain only at 100 location. Then natural question is, how about the position, for example, just in between x0 and x1? Do we have any solution at this position? Of course, in the case of an analytic approach, we can have an exact solution. However, when we work with this discretized approach, then we have no available solution. However, we will make a certain assumption that this solution psi, which is approximated in this domain, discretized domain, have smoothing bearing properties. Although we don't have any kind of information about the midpoint between x0 and x1, but we will assume that maybe we can make a good approximation by adopting something like this. Just taking certain discretized solutions and take half and half, that will give a good approximation about this solution. This is our assumption. You know, although in these days people are so much familiar with way of solving the problem using the discrete domain, sometimes people think that that is really exact one, but please don't be confused. So actually it is just a way of approximating the real solution. with the belief that if we introduce many points to discretize the domain, then maybe our approximation would be a good approximation for realistic solution. That is our assumption, and we all agree about that. Okay, so once we understand this limitation of our approach based on the discretization of domain, then we have to go to the practical issues about that. For example, how can we discretize the domain like from 0 to a? The simplest way with the number n would be just to introduce uniform grid. For a while, we will work with this uniform grid. Of course, later we can easily generalize it, this non-uniform grid. So the non-uniform grid is particularly important if we wanted to have a practical simulation. However, for educational purpose, it is good enough to just work with uniform grid. Now we understand this expression. We have the naming convention like x1 to xn. I minus 1 is introduced in that way. For example, x1 equal to 0 over n minus 1a, and the final one is n minus 1 divided by n minus 1a. So that's it. Yes, we are adopting the one-based indexing because more or less I'm working with MATLAB in this example. If you are working with a different language, then please be careful about your indexing scheme. Okay, then wave vector. Wave vector can be described as a vector of, in principle, we can think about phi 1, psi 1, psi 2, up to psi n. Now we can think about this vector. Of course, once again, if we really wanted to have exact solution, we cannot satisfy this finite number of information. In this case, for example, when we say n equal to 100, we have the solution only at 100 points. However, when we have real analytic solution, we have solution at arbitrary position. We can find the exact solution. So compared with this analytic approach, so our capability is much limited. We have to say that this 100 point is enough to describe the solution. If the solution is fastly changing inside our domain, then this 100 point would be not sufficient. We have to have once again have the assumption of a smoothly varying solution in this case. Okay, anyway, this is the way for describing our wave function. But please note that we have a boundary condition. So what was it? It was psi at x equal 0 equal to 0, and psi at x equal to a is 0. You know that x equal 0 is assigned as psi x1, and x equal to a is regarded as xn. We can say that this is denoted as psi 1 and psi n. We can find that the first entry and last entry of this solution vector is automatically 0 by applying the boundary condition. So instead of having this long expression, why don't you just having a little compact form starting from psi 2 and psi n minus 1 with understanding for psi 1 and psi n equal to 0. That is the concept shown here. Then now our positions like psi 2 or psi n minus 1, from this vector, every position, for example, any index I, this I values is I is equal or larger than number 2. So also this is equal or smaller than n minus 1. So anytime for any values of I, we can safely introduce something like this I minus 1 and I plus 1. Even when we calculate I minus 1 or I plus 1, it is just larger than 1 and smaller than n minus 2. And for this case, we have larger than 3 or equal to 3 and smaller or equal to n. The reason why I'm talking about this one is always in this case, in this index, we can find center position I and left position I minus 1 and right position I plus 1 safely. For every I can find left neighbor and right neighbor. Maybe you are curious why I am talking about this seemingly obvious quantity. However, I want to introduce a counterexample. Let's say that if we are talking about x1, then what will happen? If we try to find out the left one, what is the left one for this x at psi at x1? x1 equal to a, and there is no available point smaller than this x1. So left position is not available. Using the same argument, we can talk about xn, which is equal to a. If we refer the right position of psi n, then we cannot find any meaningful variable, because so beyond this x sub n, there is nothing. This is outside of our domain. However, since we are restricting ourselves only to the range of I starting from number 2 ending at n minus 1, we can easily find always the left and center and right position. Always they are available. Yes, this is x and happen to be this is xi, our interested position. And here we have xi plus 1, and here we have xi minus 1. Of course, we can find the discretized solution at each position. So say that, let's say this would be psi at xi minus 1, and that is denoted as, in this work, just psi I minus 1. And here we have psi x sub I, and for simplicity we will call it as just psi I. And also for certain position like x sub I plus 1, we can define psi I plus 1. If we have these three function values defined at three different neighboring position, then we can calculate this second order differentiation defined at x equal to xi. That is given here. Yes. Then how can you understand this one? Since this is a second order derivative, so then natural question is, then how about first order derivative? So let me just consider first order derivative in this time. Differentiation is actually defined as a limiting case of the ratio. So do you remember it? If we define this x, the first derivative at x equal to xi, how do you define it? In this case, you introduce, for example, small numbers like delta x, which eventually goes to 0, and consider, for example, the ratio between small differences in the function to small differences in the independent variable x. For example, this is something like this: xi plus half of delta x minus xi minus half of delta x. You know, you understand this is corresponding to slightly right side, and this is slightly left side in our axis. And of course, we have to calculate small differences in our function. For example, psi at xi plus half of delta x minus psi xi minus half of delta x. This is actually the definition of differentiation. So that then generates first order derivative. You know that in analytic solution or analytic method, we can take this limiting case. We can easily introduce this limiting case, but in the case of our discretized system, we cannot take it because we have limited resolution in real space X. So then how can we proceed? In this case, we introduce a certain limitation about our resolution. Okay, we cannot take this limit delta x equal or approach to 0. However, since we have sufficient resolution, even with this discretized system, then we argue that this quantity, like xi plus half delta x minus xi minus half delta x, and psi I half delta x minus half delta x. So this is just nothing but the definition of differentiation without the limiting case. That is a good approximation for our definition. So can we justify it? So actually we have no inherent justification about this assumption. This is exact definition, but there is no guarantee that actually this approximated ratio would be close to the real real first order derivative. But we believe that this is good enough. Then, lesson from this simple discussion is that, okay, first order derivative can be approximated by certain position and another position. They are neighbors, and the values at also those neighboring position. Then please try to find out two neighboring positions in this configuration, LCR configuration. How can you find your neighboring positions? We can easily find the pair of L and C, or C and R can be another pair for neighboring point. So in this case, if we consider the pair of L and C, then maybe the first order derivative can be approximated as psi I minus psi I minus 1. And this is C and this is L, and also xi minus xi minus 1. Since we have introduced uniform grid in this course, yes, then we can say phi I minus phi I minus 1 divided by uniform spacing delta x. That would be a good approximation for first order derivative defined between L point and C point. Then how about between C point and R point? We can also easily consider it like this: psi I plus 1 minus psi I divided by delta x. That would be a good approximation for the first order derivative between C and R. So this one is corresponding to between L and C. So now we have generated a good approximation for first order derivative defined at this range and that range. But our eventual goal is not this first order derivative, but our second order derivative. How can you generate the second order derivative? In this case, since first order derivatives are defined in between L and C and C and R, we will assume that actually these quantities are defined just midpoint of xi plus xi minus 1, and we will define another one like midpoint between xi plus 1 and xi. In this case, if we have first order derivative defined at this point and that point, or graphically defined at this point and this point, why don't you just take another derivative of this newly generated function defined at yes and yes? What will happen? If we take once again the derivative of this function, then we will say that psi over dx defined at xi plus half. This is the notation for a midpoint between xi and xi plus 1 minus the phi dx defined at xi minus half divided by delta x. That would be a good approximation for our second order derivative. For what? For which position? So still midpoint between this start position. This is at xi. When we just insert the information like this and that, then eventually we have something like delta x squared here and psi I plus 1 minus 2 times psi I plus psi I minus 1. That becomes an approximation for second order derivative defined at x equal to x sub I. So we will use this form in this lecture. Okay, so then let's go to the real implementation. So consider a case of n equal to 5. Once again, if we start from the very beginning, then we have to introduce x1 equal to 0, x2 equal to just a quarter a, 3 half a, 4 3 quarter a, and eventually ends up a, defined as x5. And also we define psi 1, which is by definition psi at x1 and up to psi 5, by definition psi at defined x5. However, by applying the boundary conditions, they are automatically 0. So therefore only meaningful entries are just 2, 3, 4, psi 2, 3, 4. We will use only a vector containing psi 2, psi 3, and psi 4 to describe our wave function. Then if we understand 3 different numbers, so real numbers, then we will say that this is corresponding to our wave function. Then how can we now proceed? So we have to evaluate the Laplacian operator at 3 different positions, like at x equal 2 and x equals 3 and x equals 4. Now we will take the discretized form of this second order derivatives. Then at x equal 2 we have something like this. Common factors squared delta x, and we have psi 3 minus 2 times psi 2 minus psi 1. That is discretized form of our Laplacian operator. Then how about this? In this case, you will have very similar one, but psi 4 minus 2 times psi 3 minus psi 2. And finally, here you have 2 psi 5 minus psi 4 minus, oh, sorry about that, here we have a plus psi 3. Now we have 3 different Laplacian operator evaluated at 3 different positions. But you know that here among them, for example, psi at x equal 1, this one is automatically 0, or psi at x equal 5, this one is also automatically 0. So more simplified form, then we have common factors here, and psi 3 minus 2 times psi 2, and this is the same as before, psi 4 2 times psi 3, yes, and eventually we have 2 times psi 4 plus psi 3 and delta x squared. Okay, then since we have introduced a vector form, then maybe the operator applied to this vector can be regarded as a matrix. So if we adopt this representation, then we have a certain vector and have matrix, so that gives us another 3 by 1 matrix. So this is corresponding to our psi, and this is corresponding to our second order derivatives, and in the case of an eigenvalue problem, this one is happen to be minus k squared and psi. Okay, so then okay, now we wanted to fill this matrix. How does it look like? From these three form for our Laplacian operator, we can generate this matrix form. So let me just write down the answer. Since we have here common factors 1 over delta x squared, I'll just put it in front of everything. Yes. Then we have just psi 3 minus 2 times psi 2. Then I will fill like this. So have number 1 here. Then this 1 generate just psi 3 because this is the way for performing the matrix vector multiplication. Then how about this? Minus 2 times psi 2. How can you generate it? Minus 2. That will give us the minus 2 times psi 2. Then how about this position? This position should be kept as 0. Then if we introduce minus 2, 1, 0, one single row, that is corresponding to the Laplacian operator evaluated at x equal to x2. Then why don't you just place the Laplacian equation evaluated at x3 into the second row? You can easily do it. So psi 4 is corresponding to number 1. Minus 2 psi 3 is corresponding to minus 2. And psi 2 here is corresponding to positive 1. Finally, if we repeat it for the Laplacian operator evaluated x4, then we will have number 2, 1, and 0. Now we are arriving at this position. Laplacian operator maps the above vector into this form. Now this is correspondence. This is our wave function. This vector, solution vector, is corresponding to our wave function, and this matrix and coefficient is corresponding to our second derivative operator. So it can be regarded as a discretized version of a second order derivation. Then let's try to solve eigenvalue problem. Now we understand previous one is an eigenvalue problem. In order to really solve this problem with computer, so for example using MATLAB or Python, C++, Fortran, whatever, we have to learn how to solve eigenvalue problem with computer. So we will start from just 2 by 2 example. Let's say that we have a matrix which is given by 2, minus 1, minus 1, 2. How can you obtain the eigenvalue or eigenvector of this matrix A? Then we have to calculate this one, a minus lambda I. So this is corresponding to 2 minus lambda minus 1 minus 1, 2 minus lambda. And its determinant should be 0 for this case. Then determinant is 2 minus lambda, 2 minus lambda, minus 1, minus 1. So this is nothing but lambda minus 2 squared minus 1 equal to 0. So we will have lambda minus 2 equal to plus minus 1. So what will happen? Then lambda can be 3 or 1. That is the solution. We can do it by this way analytically. However, we wanted to ask the computer to solve it. Then let's first work with our MATLAB program. Okay. For that purpose, I have prepared my MATLAB session here. Okay. Here, we have nothing right now. Then let's define a matrix. So its component is 2 minus 1 minus 1 2. I just lead it in this direction. Then now we have a matrix, and this is just memorized by MATLAB. Then how can we obtain the eigenvalue and eigenvector? There is a function in MATLAB function called EIG. So it takes on matrix A as its argument and generate the eigenvectors and eigenvalues. So here V is corresponding to eigenvectors and D are corresponding to eigenvalues. Why don't you just type it? Then now we find that, okay, eigenvector is given by this one, minus 0.7 minus 0.7. This is corresponding to one vector, and another vector is minus 0.7 and positive 0.7. These are two different eigenvectors, and their corresponding eigenvalues are 1 and 3. Okay, 1 and 3, this is the answer we wanted to have. Yes. So, of course, this is just the example for MATLAB uses, and you can try to do the same thing with different languages. This is up to you. Please perform the same exercise with the language of your preference. Now, why don't you solve infinite potential well problem? Then infinite potential problem is now casted into really simple form. Okay, here this is nothing but second order derivatives, and psi happen to be equal to psi multiplied by minus squared k. Then how can you solve it numerically? That's easy. We have just a matrix and psi, and we will just bring our 1 over squared delta x to the right hand side, and then delta x squared k squared, and we will have once again psi vector. So this quantity can be interpreted as eigenvalue of our system. since we need only matrix for eigenvalue problem, we will use only this 1, 2, 1, 1, 1 minus 2, this one as a matrix. Then we will have certain eigenvalues, and by interpreting as eigenvalue with a sufficiently good number for delta x and k equal to n pi over a, by using this information we can really find out the k values out of this normalized eigenvalue. Our goal is now reduced to find out the eigenvalue of this 3 by 3 matrix, and its diagonal component has all number 2 minus number 2, and its off-diagonal component, certain off-diagonal component has positive 1. Then let's do it together. So first clear, then there is nothing. This is given by minus 2, 1, 0, 1, minus 2, 1, and 0, 1, minus 2. So just enter. Okay, now we have a matrix, and this is the correctly entered one. Then why don't we just call once again this function, EIG function, with an input parameter of matrix A. Then we will get the solution. When we type enter, okay, we find eigenvalues like minus 3.4 and minus 2 and minus 0.58, and this is corresponding to 3 eigenvalues. Then what is the meaning of this number? Please remember that actually our lambda obtained from matrix solution can be interpreted as delta x squared and k squared. So therefore, if we insert proper values of delta x, then from these lambda values we can find the value of k. Then actual estimation of physical validity of this lambda is up to you, and please check it. Okay, this one contains the physical interpretation of eigenvalues, and please do it by yourself. Yes, this is also introduce some practical numbers, and for example here we have number A equal to 5 nanometer. 5 nanometer is really practical values. In this course we are considering certain system looks like this. So silicon slab, and its thickness is just 5 nanometer or around, and its width is much larger than 5 nanometer. That is the system of our interest. Here number A is corresponding to the vertical direction confinement. Here we are now talking about the vertical direction view, and when we introduce mass of 0.91 times electron rest mass, we can find a certain physical interpretation about these numbers. So this is also up to you. Please read it, and if you have questions, please let me know. Okay, so this is the end of our lecture 2, and I wanted to say we have already homework number 2. So you have already made your subfolder and upload your code and report in your subfolder. And due is this Wednesday, just before our lecture 3 start. And this is, the goal is write a simple code solving infinite potential well problem. In this case, effective mass is just 0.19 m0, which is corresponding to electron rest mass. And use 3 different values of n, 5, 50, and 500. You can easily solve the problem. So let's wrap up the lecture 2. See you. Bye.